Okay, so next we're going to speak about a very cute problem of how to compute the longest increasing subsequence. So a few definitions before we get too far afield. So a sequence is, of course, it's just a sequence of elements, A1, A2, and so on until AN, which are numbers. You can think about them as being stored in an array or in a list. A subsequence is just a subset of the sequence. We already encountered that when we spoke about strings. And a sequence is increasing if, as we read the element in order, the number keep increasing, right? And it's a bit painful. So usually you speak about non-decreasing, where you mean that they might also be equal. Similarly, you speak about decreasing or non-increasing, right? But for sake of simplicity of exposition, let's just think about increasing sequences here. Okay, so let's see a few examples. This is a sequence, right? And you can find a subsequence, for example, 5 to 1, right? We take those elements, which is equivalent to deleting all those elements. So that's fine. And then, this is an increasing sequence, the numbers go up. This is a decreasing sequence because the numbers go down. And of course, we can speak about increasing subsequence of the original sequence, right? Which in this case would be, 3, 5, 7, 8, 9, right? So this is 3, 5, 7, 8, 9 is an increasing subsequence of the original sequence. Okay, so the problem is the following. I give you a sequence, and the goal is to find an increasing subsequence of maximum length, right? Okay. So I think I already showed you the optimal solution in this case, but 2, 7, 8 would be one possible subsequence. 3, 5, 7, 8 would be another one. I think for this specific case, this is the optimal one, right? You cannot do any better. And the question is, of course, how do you compute this longest subsequence, and how do you do it efficiently? So, of course, the most naive algorithm is just to try all possible subsequences, right? So if we have n elements, there are 2 to the n subsequences, and for every such subsequence, we just check if it's increasing or decreasing, right? Well, if it's increasing, because we care about the increasing one, and then we keep track of the longest subsequence we found and we return it, right? And that, of course, is a terrible algorithm. Congratulations to us, we came up with a terrible algorithm. The running time is there are 2 to the n sequences, and we have to try each one. We have to spend linear time verifying that it's increasing. So that's the running time. Now, we can do much better, but before I go any further, I would like to say that, whenever you face an algorithmic problem and you want to think about it, first thing that you should do is think about the naive algorithm. And the naive algorithm always provides you a floor from which you can build up on. And the big mistake is that you don't even have a naive algorithm, and then you start building more and more complicated things, and it's like building castles on sand. So always come up with a naive algorithm, understand the basic properties, and then try to do better, right, by optimizing things and so on. Okay, so what is going to be our idea? Our basic idea is that we are going to define a recursive algorithm, right? And it's going to have the array, if you want, the sequence that we are looking at. And now we define 2 possibilities, depending on whether or not we take the last element. Right? So if this is the sequence, right, we have AN, this is the last element. We either take it or not. If we don't take it, we just need to recurse on the first n minus 1 element in the sequence, so we just call it recursively. Case 2 is we decide to take it. right? So that's good. And then it's not clear what to do, right? Because you cannot quite recurse on the prefix, because if to see why, think about the number written here in the last cell, right? The last cell might have the number 7, right? When you solve the problem now for the prefix, if we decide to take 7 to our subsequence, we cannot take numbers like 9 because it's too large, right? So we need to pass on to the recursion the constraint that says, oh, you cannot use number bigger than 7, right? So this is part of the thing that we need to kind of pass information down. And so we need to kind of modify the problem. And by the way, this is a standard trick that we have a problem and somehow we define a recursive procedure or recursive function that have some additional information we need to carry around, right? So we're going to define this modified function called least smaller, longest increasing sequence smaller, which again receives a sequence or an array to search for the longest increasing sequence, subsequence, but none of the elements is allowed to be bigger than x, right? Okay. And now the dynamic program becomes quite simple, right? Because if it's an empty sequence, you return 0, because what you return is the longest sequence. Otherwise, there are two possibilities. Either you don't take the nth element, so then you call recursively, and you keep the constraint that the element have to be smaller than x. Or alternatively, if the nth element is smaller than x, then you can use it. So you check the possibility of calling recursively on it, except that now in the recursive call on the prefix of the n-1 element, you pass an as the new constraint. You must be smaller than an, right? And then this is the price of the resulting solution, and you take the maximum with the previous one and you output it. So this is the algorithm. And you return, and the outer function just called this inner function with the constraint of infinity, because initially we don't have any constraint. Okay.